Hi, this is Mrs. Basin, and today we're going to talk about uncertainty in measurement. So when you're doing any kind of measurements in science, there's always some degree of uncertainty or error that's associated with them. And those errors could be attributed to two main things. One could be the person actually doing the experiment, and the other error could have something to do with the device that you're using to do the measuring. So when you're talking about measurements, there's two words we can use to describe these measurements. We can talk about the measurements, the accuracy of these readings, and we can talk about the precision of the readings. So accuracy has to do with how close the measurement is to what the actual or true value is. Precision has to do with how close the measurements are to each other. So if you take a series of measurements, you are precise if those measurements are all fairly close to one another. Whereas again, accuracy has to do with how close is the value to what you're actually supposed to get or what the actual value is. The classic example that they use for this is a dartboard to describe this. So my first example here, letter A, or dartboard A, has low accuracy and low precision. So they threw 3 darts. They all ended up all over the place. So accuracy in this case would be the bullseye. So none of them got even close to that. So low accuracy and low precision because they all 3 of them ended up in different places. Now if we move to letter B has low accuracy because they're not anywhere near where they're supposed to be, but there's very high precision because all 3 of them ended up in the same place. So when you're doing a lab, if you have low accuracy but you have high precision and you're continuously getting the incorrect value, that can sometimes tell you that there could be something wrong with the piece of equipment that you were using. For example, maybe a balance needs to be calibrated, and that's why you're not getting a correct value for your answer or for your measurement. Letter C has high accuracy because they're all fairly close to the bullseye where they're supposed to be, but low precision because they're kind of all over the place. So they're not all close to the bullseye in the same place. And then finally, this is what we're looking for. This one has high accuracy because they're where they're supposed to be, and it's high precision because they all ended up in the same place. Percent error is something that we can use to look at the difference between the accepted value and our experimental value in the lab. So the experimental value is the value that was measured during the experiment. So it's the value that you obtained when you actually did the experiment, when you took the measurements off the balance or off the graduated cylinder. That's your experimental value. It's the one you obtained while you were doing the experiment. The accepted value, which is sometimes also called the theoretical value, that's the correct value that's based on agreement with a reliable reference. So the accepted value is what you are supposed to get. Now, sometimes we'll do a lab where you don't know what the accepted value is, so you're not always going to be able to do a percent error, but if it's something where you know what the value is supposed to be, then you can calculate your percent error to kind of give you an idea of how close you were to what you were supposed to be. So when we calculate percent error, we take the experimental value minus the accepted value, and notice this is an absolute value, so if that ends up being a negative, we just drop that negative there. And it's divided by the accepted, and then times 100 to make it a percent. Ideally, we want a low percent error. So the closer we are to the accepted value, the lower our percent error is going to be. Okay, so here's a practice problem for us. It says we have a student that measures the mass of a solid sample to be 8.09 grams. The accepted value, or the correct value for that, is 8.42 grams. So we want to calculate our percent error. So all we have to do here is we're going to do percent error equals absolute value of our experimental, which was our 8.01 grams, because this was what was measured in the lab. That's how we know that's our experimental. So 8.09 grams minus our accepted value, which is 8.42. And this 8.42, the accepted value is going to come from a reference, from a table. You'll get that from me. So the accepted value you're going to look up somewhere compared to, again, the experimental coming from the experiment. Then we're going to divide by the accepted value again, which was 8.42, multiply by 100, And our percent error then in this case, it's going to turn out to be a negative, but we're going to drop that negative just like we said because that's absolute value. So we end up with a 3.92% error, which that's a pretty good value for a percent error. That's a pretty low percent error, which is what we're looking for. Okay, the last thing we want to look at in this particular section are significant figures. So we're going to start with a real quick review of this, and then we'll kind of go through and do a few practice problems. So what significant figures has to do with is it refers to the digits that were measured. So it signifies what kind of a measuring device was used. That's why these are so important. So when you round calculated numbers, we pay attention to significant figures so we don't overstate the accuracy of our answer. So if you're using a piece of equipment that only measures to say the tenths place, you can't have, when you calculate those values, you can't have an answer that is more accurate than the least accurate piece of equipment, if that makes sense. And we'll kind of look at that in just a second here. So here's the difference. This is what we're talking about. If we use this one at the bottom here, so if we use this piece of equipment right here, this measures to the ones place. So if you remember when we talked about measurements before, when you take a measurement, you always estimate one place past what the device measures. So if this ruler measures to the ones, which would be this place here, then we're going to estimate the tenths. So if this is where our measurement fell here, we know it's between 2 and 3 for certain, and we're estimating that 0.5. We're estimating how far we think it is between those two. So 2.5 would be our value for this one down here. And let's say we're measuring centimeters here. This top one, notice that it's still the same length, but now we have an extra digit here. That's because this piece of equipment up here measures to the tenths, because now we have marks here in between. So that means we have to estimate to the hundredths place. So we know for certain it's somewhere between 2.5 and 2.6. We're estimating this last value here. So with any piece of equipment, whether it's a ruler or a graduated cylinder or a burette, whatever it is you're using, you always estimate one place past what it measures. So if the lines go to the tenths, you estimate to the hundredths. If the lines go to the ones, you estimate to the tenths. Okay, so here's another example. So we have two graduated cylinders here. This one measures to the ones. So if I was going to estimate, if I was going to take a measurement from this particular graduated cylinder, I know for certain it's between 4 and 5. So I know it's going to be 4 something. So I'm going to call this, let's say, 4 point, it's a little over halfway, so let's call this 4.7 milliliters. So that's how we would record this. So this would have two significant figures because we know for certain the 4 and then we're estimating that 7. Now, if we look at the same amount with this graduated cylinder, now we have a little more information here. So now this time, if we count, there's 1, 2, 3, 4, 5, 6, 7 little marks there. This time we know for certain it's 4.7, and then it's in between 4.7 and 4.8. So this time I'm going to estimate the hundredths place. So I know this digit for certain, I'm estimating this. We're still going to call this milliliters. So when you record these values, how many decimal places you record communicates to the person that's reading that, and it tells them something about the piece of equipment that you measured. So if you were using this graduated cylinder and you only recorded 4.7 milliliters, you'd be misleading that person and communicating that you were using a graduated cylinder that looked more like this than one that looked like this. So this would be an incorrect way to write that. If you're using this piece of equipment, on the right here, you would have to include that hundredths place. Okay, so here's a real quick review of significant figures. The first one is all non-zero digits are significant. So anything that's not a zero counts as a sig fig. So say 25, that would have 2 sig figs. Zeros between two significant figures are significant. Before, I think we call these captive zeros. So if you have something like 205, that zero counts because it's trapped between two non-zero numbers. So that would have 3 sig figs. Zeros at the beginning of a number are never significant. So if I have like 0.0015, these zeros in the front don't count. I don't start counting till I hit that non-zero number and then count everything afterwards. So this would have 2. Zeros at the end of the number are significant if there's a decimal point. So let's say I have just 150. That 0 is not significant because there's no decimal, so this number would only have 2 sig figs. Now if I put a decimal point there, now that makes that last 0 significant, so that would give me 3. Another way, if I wanted to show 3 sig figs with this, is I could put this into scientific notation. So if I did this, this also has 3 sig figs, because when you have scientific notation, anything in front of the time sign counts. Last example here, let's say we have 0.00150. Okay, so in this case, the leading zeros don't count, but like we said earlier, once you hit this 1 here, everything past that counts. So this would have 3 sig figs. So this 0 counts after the non-zero number after a decimal. Okay, so let's do a little bit of practice. That's the easiest way to do this. So if we look at the first one, this first one, those leading zeros don't count. We don't start counting until we hit that 9, so this would have 1 sig fig. Okay, and my second one, the leading zeros don't count, but once I hit the 9, everything else behind it does, so this would have 3. These are all non-zero numbers, so that also has 3. These, all of the numbers except for that last 0 count, so this would have 1, 2, 3, 4, 5. This one, that's a captive 0, all of those count, that would be 3. This one, only the 4 counts because there's no decimal there, so this would only have 1. And in scientific notation, anything in front of the time sign counts, so this would have 2. Okay, when you're doing calculations, it depends on whether you're adding or subtracting or multiplying, dividing. Now most of the time in here we're going to be doing the multiplication division rule, but just as a quick review, we'll talk for just a second about addition subtraction. So when you're doing addition subtraction, you round to the least significant decimal place, or the lowest number of decimal places. When you multiply or divide, you round to the number of digits that corresponds to the lowest number of sig figs and any of the numbers used in the calculation. So you round to the smallest number of sig figs. So we'll do a couple examples here. So for this one, how many sig figs are in the following summation? So if we added all of this up, we would end up with 132.220. Okay, and then we're going to look at what we're adding here, and we're rounding, since we're rounding to the lowest number of decimal places. So this has 3 decimal places, this has 1, this doesn't have any, so that means our answer has to be rounded to the nearest whole number. So this one can't have any decimal places. So this would be reported as 132 with no decimal places. And that again is because this number here limits the number of decimal places we can have. Okay, now this one has adding, subtracting, and division. So we're going to follow our rules for what you do first here for orders of operation. So I would do this part first. So over here I end up with 1.70. Now I'm going to keep that last one there because they both have 2 decimal places. So I'm rounding to 2 decimal places. Then I'm dividing by 2.734. So when I get my answer here, I'm going to round to the lowest number of sig figs, which is 3, like this one. This one has 4, so I'm going to round to 3. So I round my answer to 0.622. Or to answer this, how many sig figs should the following have? It should have 3 sig figs. Okay, my last example here is another multiplication division problem. So this one, how many sig figs are there in the result of the following multiplication? So if I'm multiplying, I have 3 sig figs here, I have 2 here, I have 5 here. So since I'm multiplying, I round to the lowest number of sig figs, which would be 2. So I'm going to round this answer to 2 sig figs. So if I go ahead and do this calculation, I end up with 188.976. So if I'm going to round this to 2 sig figs, I have to round it to this place here, so I would round this to 190.